Okay. Good morning, afternoon, and evening for the audience of this video. My name is Faraz Ezra with student ID 136180051. Um, in this opportunity, I want to present about my reconstruction on MAVEN mission for astronautics assignment. MAVEN is Mars Atmosphere and Volatile Evolution. This is a mission which intended to observe and examine Mars condition on its atmosphere. This mission is carried out in 2013, and today I want to present the reconstruction of the mission. In this case, the reconstruction consists of three phases of the mission. First is the launching, park, and escape from Earth gravitational effect. The second is the transfer from Earth to Mars in its heliocentric trajectory. And the third, the final, is the capture and arrival on Mars orbit. The data used for this analysis is the mass of the rocket and the spacecraft in the launching, and also the specific impulse of the propulsion system, and also the trajectory geometry designed according to the data. The purpose of this reconstruction is to compare the elapsed time on the transfer phase and also the propellant mass used for the mission. Let's look on the launching. MAVEN is launched at Cape Canaveral Air Force Station at November 18, 2013 in 1828 UTC. It was propelled using Common Core booster carried out by Atlas V rocket, which has specific impulse 325 and 0.15 seconds. The objective of the launching phase is to reach parking orbit with a radius of altitude 241 kilometers. The assumption used is to assume the specific impulse has the same value along the launch trajectory. Okay, so the intended speed in its parking orbit by using Fish-Viva formula is 7.763 km per second, and the initial mass in launch phase is the sum of the rocket mass and the spacecraft mass, which is around 337,000 kilogram. After we calculate the final mass by using Tsiolkovsky equation, we obtain the final mass around 30,000 kilogram. Therefore, the propellant mass used is 307,000 kilograms. According to the data, the CCB spent 257,000 kilograms of propellant. After the spacecraft reaching the parking orbit, next we have to consider what is the design heliocentric trajectory along the transfer orbit. If we take the Earth as the perigee and Mars as the apogee, which is not a base assumption, but we could use that condition, we could obtain the radius of the perigee, apogee, and semi-major axis, and also the velocity intended in each position, which is we could calculate the perigee and apogee velocity, or which is the velocity in the Earth and Mars is 33 km per second and 22 km per second, respectively. After we obtain the designed heliocentric trajectory velocity, then we could calculate the escape velocity that we have to achieve using the propulsion system. Shortly after reaching its parking orbit, the Centaur rocket propels the spacecraft to escape from Earth's gravitational influence. By its specific impulse to 450 seconds, the propellant mass used for this phase is around 17,000 kilograms. By that propellant, we achieve a velocity increment to 3.6 km per second. After those propellant mass is used, the spacecraft is now going on its heliocentric trajectory on its way to Mars. The time elapsed between Earth and Mars capture is equal to the half of the orbital period, which could be calculated using third Kepler law, and we could obtain that the time elapsed is 159 days. Actually, the elapsed time is 308 days. It is a bit longer than the calculation because, as we can see on the sketch of the trajectory, the Earth and Mars is not perfectly on the perigee and apogee position. Instead, the path taken is longer than half of the orbit, so it elapsed more time than the calculated, which using the assumption of perfect ellipse. In the capturing process, the intended capture orbit is having an altitude of 380 kilometers. Therefore, we could calculate the intended orbit velocity using Vis-Viva integral is 3.4 km per second. From the heliocentric trajectory, we could calculate its relative velocity to the Mars orbit, and we could obtain its excess hyperbolic velocity, or V infinite, which is 2.23 km per second. By using hyperbolic formula, we could obtain the hyperbolic perigee velocity equals to 5.26 km per second. Therefore, the velocity decrement that we have to achieve is equals to around 1.9 km per second. By achieving that using inboard propulsion system with specific impulse to 130 seconds, we need to use propellant mass until 1,400 kilograms. Okay, all of the phase has been calculated. Now we can combine the data and compare it with the actual data. The propellant mass used in its launching process is as follows, represented on the table. As we can see, the error resulted is 19.3%. For the propellant mass that used to escape the Earth's gravity, the reconstructed calculation and the actual data has the difference of 13%, and for the capturing process, the error resulted is 12%. Overall, the error generated is less than 20%, so that the calculation is pretty close with the actual condition. However, this was caused by the assumption used in the reconstruction process, which is a perfect elliptical trajectory from the Earth to Mars, and also the uniform specific impulse value along the launching trajectory from Earth's surface until Earth parking orbit. And also maybe there are some miscalculation along the reconstruction. Okay, that's all from the presentation. Thank you for the attention. I would also like to apologize if there are any miscalculation or any mistakes in the analysis. Thank you very much. Any feedback will be very welcome.